Watch a large language model attempt a complex multi-step task, and you'll see a structure that builds flawlessly for a moment, and then collapses. The failure is not in the reasoning of the individual steps. The failure is statelessness. The agent lacks an internal tether to carry logical consistency from one action to the next. This equation defines an agent's baseline policy. Pi theta represents frozen parametric knowledge, and OT is the immediate observation. Both are fixed. To carry logic into a dynamic environment, we need this variable, MT, the context-specific memory, an empty void we must architect. The approaches to filling this void are currently fragmented. One faction engineers operating system pipelines to manage data limits, while another attempts to simulate human cognitive psychology. Solving the statelessness problem requires a unified view. We can formalize the development of agent memory into a single three-stage evolutionary taxonomy: storage, reflection, and experience. Autonomous evolution depends on a structural change in how an agent processes, refines, and eventually abstracts its own historical trajectories. The foundational layer of this architecture is storage. At this stage, the system's sole objective is the high-fidelity preservation of interactions. This equation formalizes raw storage. It records memory as a trajectory, a strict chronological sequence of observation and action pairs written to the drive exactly as they occurred. To process this massive influx of logs, engineers utilize linear context windows, vector spaces, and structured topological networks. But relying purely on storage introduces a severe mathematical bottleneck. As an agent operates over long horizons, its memory expands linearly. Any hallucination or flawed logic recorded early on remains in the log, propagating outward and permanently contaminating the context window. This diagram illustrates a timeline of environmental states, exposing a flaw known as the temporal validity of knowledge. When the environment shifts causality over time, a standard vector search will frequently retrieve an action from a past state that was correct then, but is disastrous now. The retrieval system assigns the old data a high score because the text matches the semantic request perfectly. The agent pulls factually obsolete information without triggering any explicit error code. Pure trajectory preservation fails in a real-world deployment. To survive dynamic environments, the agent requires an architecture that actively evaluates and edits its own history. This requirement moves the architecture into the reflection phase. The memory module transforms from a passive recording drive into an active, self-correcting critic. This equation represents a semantic transformation. The agent takes a raw, noisy trajectory sequence, passes it through an evaluation criteria filter, and generates a refined, high-density memory node. Agents perform this filtering through three mechanisms: introspection, utilizing the model's internal critique; environmental anchoring, based on external feedback; or coordination, where collectives establish consensus. Reflection successfully cleans the data, yet it introduces its own failure mode. These corrected memories remain highly episodic. They are mathematically tethered to the original task context. Language models over-index on past successes. Deploying a refined memory into an altered environment causes the rigid contextual memory to induce entirely new reasoning errors. Perfecting the data quality of a past event does not guarantee generalization to a future one. To operate autonomously, the agent must learn to detach the operational rule from the specific scenario. Detaching the rule brings us to the final evolutionary stage, experience. Here, the system shifts from refining a localized trajectory to abstracting patterns across multiple trajectories. The experience phase operates on the minimum description length principle. The mathematical objective is to compress massive batches of redundant interaction logs into the smallest possible representation. The equations for this phase show the agent isolating topologically similar paths. From this chaos, it extracts a clean, universally applicable rule set, K, that requires a fraction of the original storage space. Because this compressed rule set is a synthesis of many past successes, it functions as a policy prior. Unlike reflection, which searches for a specific context match, this prior acts as a pre-existing intuition. It guides the agent's initial strategy in a completely unseen environment before the agent has even performed its first action. By abstracting rules from raw data, The agent eliminates the immense compute cost of retrieving historical logs line by line. It replaces brute force search with generalized intuition. Extracting these universal rules requires the model to process data across distinct levels of abstraction, measured by how far the output deviates from standard natural language. At the explicit layer, the agent distills grouped trajectories into human-readable text policies, or modular code functions. These encapsulations act as a highly interpretable, reusable skill library. At the deep implicit layer, natural language is stripped away entirely. The agent internalizes the experiences directly into its latent network and gradient weights, completely embedding the behavior into the model structure. Between these two lies the hybrid approach. The system creates a dynamic cycle, caching explicit code rules for immediate short-term use and periodically compressing them into the model's implicit parameters to eliminate inference overhead. Whether it stores the lesson as an executable Python script or as updated parametric weights, this cross-trajectory abstraction is the mechanism that separates a static language model from an evolving agent. With the experience architecture in place, the system's behavior changes. It transitions from a passive respondent, reacting to prompts, into an active explorer, driven by intrinsic motivation and targeted reward signals to seek out new data. The entire process locks into a continuous autonomous loop. Active exploration generates the data for storage, reflection cleanses the noise, and experience synthesizes the policy priors that guide the next round of exploration. Scaling this loop introduces immediate bottlenecks for researchers. Systems require active memory perception, giving the agent the ability to autonomously trigger retrieval only when a task demands it, rather than indiscriminately loading context and flooding its own reasoning. As we move toward multi-agent organizations, relying on explicit dialogue to share data will choke the bandwidth. These organizations will require distributed shared memory, silent, consensus-based systems that synchronize collective knowledge without explicit communication. The era of patching pre-trained models with external vector databases is hitting a point of diminishing returns. Building the next generation of agents means engineering architectures that natively translate raw storage into the weight of experience.